Let's have a look at vertical circles. Vertical circles are the tricky bits, and it's pretty crap. Sorry about that, but we'll change to when we get there. So often we have a little car, if you like, at a certain height, and what we do is we say, if this little car comes down, right, he's got energy, he's got mass, he's got potential energy of mgh. And when he gets down to the bottom, that potential energy is going to be converted into kinetic. So at the bottom, he's got a speed, right? Or a velocity. And then he's going to be forced to go in a circle. And that circle's got a radius r. And so he's going to need a centripetal force. So we're going to look at the forces. But first, let's just make sure we remember how to calculate the speed at the bottom. We say that the potential energy has all been converted into the kinetic energy. So we say that mgh now equals half mv squared. We cancel the m's and we say that v equals the square root of 2gh, right? Remember that from year 11? So that's the speed he'd be doing at the bottom there. Now, let's get ourselves another bit of paper because that one was rubbish. I'm usually pretty good at circles. If we get that car at the bottom, he's come from up that great height, remember? He might go down there afterwards, or he might just keep going in circles. What are the forces on him? Now we know he's normally got a weight force. Well, normally, always. Right? And so there's always a support force, equal and opposite support force. Okay, Fs. But we just worked out that he had a velocity at the bottom of square root of 2gh. Right? So that means he needs a centripetal force of mv squared over r being that one. So we now know that he actually needs this one here, this v squared here, would be equal to 2gh, obviously. So he needs m 2gh over r as an additional force on top of this vector here when he's at the bottom there. And the reason he needs that is because the support force gives him nothing. It gives him no centripetal force. It basically just keeps him sitting there. So we need a little bit of extra force to make him go in a circle. Depending on how fast he's going, how much force that is, you'd have to work it out. Now, the thing is that where does that come from? It must come from the rails. So we call that reaction force from the rails. So that reaction force is going to equal mg plus 2mgh all over r. That's how big this vector here is. Alright? Now, another thing we often do in these examples, whoops, running a bit low on paper. Another thing we often do is we go, well, what about at the top? Well, this little car, he's gone up to the top. All very good. Now, at the top, things change quite dramatically because now his mg is down. So his mg can actually supply some of the centripetal force. And in fact, there's a point at which, and this is the minimum speed to get round, there's a point at which the mg can supply all of it. Minimum, speed to get round is when mg supplies all the centripetal force. Right? So at that speed, you'll still get round, you still won't fall down. Mg will be supplying all your centripetal force. That means there's no reaction force from the rails. So we can say at that point that mv squared over r equals mg. We can cancel the g's and we can say, okay, rg, v equals the square root of rg. That's the minimum speed. If you're going faster than that v there, all right, can you see that? You can't quite see it, can you? Sorry. If you're going faster than that speed, v equals square root of rg, then you're going to need a bit of reaction. So if v equals square root of rg, say it was 10 meters a second, if you're going 12 meters a second, you're going to need a little bit of reaction force. That mg, though, will supply the centripetal force to go round at that speed. And that's the minimum speed that you can go round one of these loops, and we're often going to use it. In fact, we'll use it to figure out G with the buckets. We'll do that practical. In the in-between bits here, it gets a bit trickier, and that's mainly, we don't see questions like that, but we do them in scholarship. But what you've got there, you've always got your mg down, right? You've always got a reaction force that's towards the center of the circle, because the rails are always pushing perpendicular in a perfect circle. So you've got these two forces, and so you end up with this net force that's got two components. Now, if it's got two components, it's got a centripetal component that pushes towards the center, and it's got a tangential component which pushes in the direction of the velocity. Remembering that when something goes in a circle like this, its velocity is always at a tangent. So when it gets there, its velocity is like that. When it gets there, its velocity is like that. Gets there, its velocity is like that. But it's changing, right? So if its velocity is changing, the centripetal force is changing, and the centripetal force is necessary. But the only thing that can change a force in that direction, change a velocity at a tangent, is a force at a tangent. And that's because the component of mg now, the weight force, doesn't just point either towards the center up or towards the center down. Some of it is pointing at a tangent to the direction it's going in, and that's the bit that slows it down. So vertical circles get a bit tricky.